So greetings, everybody. It's it's good to have you here. We're going to be talking very, very quickly today about a number of different topics. So hold on to your seats because we're going to go through this relatively quickly. As I mentioned before, the last time I thought we were supposed to meet, it was vacation, and I thought we only had off one day, but we had off 2 days. So therefore, I'm actually a lecture behind in my schedule. So let me go ahead and share my screen. We talked about last time using steepest descent and airback propagation, a beautiful algorithm. And I wish we had time to get into the other algorithms that are variations of this or extensions of this, including in fact, all of the modern AI. But we talked about momentum. And the idea is that steepest descent is when you replace a weight in a neural network, and then you go through a step size and then a delta, and this delta is determined by the direction downhill, and this direction downhill decreases your error between what you want and what you got. We said in order to perform better, sometimes there's a momentum term added in where your next step is a little bit aware of the last step you took, so you don't jerk all around. There's many cases where this is very advantageous and it's used quite a bit. I'll give you one. Imagine that we have a search space like this, and this green line is a slight incline that you can roll a marble down. It's kind of a valley, if you will, but this valley has an end right here, and this end is the minimum. And we have contours here. And what would happen if you applied steepest descent here? This is something called cross stitching. What would happen is you would go back and forth and back and forth and back and forth, and you would actually go down the hill, you'd overshoot, you come back, you do something something similar, and you go back and forth between the two sides of the hill if you did steepest descent, because in each case you're going downhill, right? You're taking a step downhill. If you add momentum and make sure that your next step is in the same general direction as your previous step, this cross stitching is mitigated and you have more of a smooth operation to your minimum. And the momentum idea is very helpful in um, in avoiding situations like this. Now, you always don't have this sort of valley, but cross stitching is something which is very uh, well, it's prevalent. It's a problem in neural network training, and so we have to be aware. We have to be cognizant of that. We talked about last time avoiding the curse of dimensionality. We showed that as the dimension of the input increased, that the number of training data that we have, it's a rule of thumb, it isn't absolute, but the number of training you had actually increased exponentially with the number of your inputs. That's the reason in early neural networks you couldn't train pixel by pixel. And if you were trying to figure out the difference between sumo wrestlers and basketball players, you would have to talk about features. And that example was height and weight. So the height and weight pretty well differentiate sumo wrestlers from basketball players. And you would use these two inputs, height and weight, in order to do the differentiation, as opposed to putting in individual pixels of pictures of basketball players and sumo wrestlers. And this is feature selection, feature extraction. We'll go into feature extraction. Feature selection is when you have a bunch of when you have a bunch of features and you have to choose the best features. And interestingly, the best features, the best set of features, are always not the best set of features. Let me give you an example. If you were trying to choose a baseball team and you wanted the best players without regard to their contribution to the team, you might end up choosing all outfielders, and that wouldn't be good. You have to choose players which give you the diversity of your baseball team. You can't choose all the same sort of players. So that's the same thing with feature selection. Now, this was mitigated by deep convolution neural networks, which I'm about to explain. Deep convolutional neural networks mitigated the problem of the curse of dimensionality and allowed us to look at images one pixel at a time. And convolutional neural networks are going to be introduced through image processing. Some of you have had Dr. Schubert's course on image processing, and you know some of the things you can do to images. So let me give you an example here. Here's a picture of a woman. This woman happens to be my wife at the time I married her. And what if you wanted to take this image and you wanted to do something like do edge detection? You wanted to outline all of the edge detection. So what you would do is you would run it through something called a Sobel edge detector. And you would use this Sobel edge detector to run across in a 3 by 3 pixel, just run across. And every time you took this summation of pixels and you replaced the original pixels with whatever this summation was, you can see that this pixel actually emphasizes pixels on the right and de-emphasizes pixels on the left. And so what happens, this is kind of like a derivative if you think about it, right? So you're taking the value a little bit to the right, you're subtracting the value a little bit to the left. That kind of gives you a derivative. And if you think of a derivative, that's a good way to get an edge detection. And that's exactly what is used with the Sobel edge detector. And this first one is G sub X. That is a horizontal edge detection. And there's G sub Y, which is kind of this thing turned sideways if you want the other edge detection. And you could do this with other windows too. For example, suppose I wanted to blur it. Instead of using the Sobel edge detector, I would use maybe a larger window and just sum up all the pixels, have all the weights the same, and replace the pixel in the middle by the average of all the surrounding pixels. And that would give me a blurred image of what happens. And so this is an example of a blurred image where we run a 3 by 3 window across. And again, we take the 3 by 3 pixels, we replace the pixel in the middle by the average, and that gives a blur. So you can see this idea of windowing is very good in terms of doing some some interesting things. But the thing is this is something which is determined by a human being. Sobel, I don't know who Sobel was, but he was the one that introduced the Sobel edge detector. And we have his namesake now for the Sobel edge detector. Now, here's the question. Suppose that we didn't know what the window was, but we wanted to learn the values in the window. You get the idea? We don't have a human there, but we wanted to learn the values within the window. So what we would do is come up with a convolutional neural network. So here's a convolutional neural network. So we have a picture of a plane here on the left, and what we're going to do is we're going to run a window across it. We're going to run a window across it. Now, what are the weights of the windows? We don't know. We're going to train those weights of the window using error back propagation. And so therefore, we don't have to worry about the entire dimension of the input. We just have to worry about the dimension of the little sliding window. And that's what the convolutional neural network does. We are training the values within the sliding window in order to determine the best way that the neural network works. You notice this takes away the curse of dimensionality. We don't have 1,000 or a million pixels here. We only have the input is just the size of the window. So we run the size of the window, and you'll notice here it's not clear, but this layer can actually be 3 layers deep, and we have a 3-layer window, and those different layers are RGB, so you can do color images. But you collect all of these things and you replace it with a new image. Then you take that new image and then you do something called you pool it. Now, what does pooling mean? Pooling means that maybe the image you get by doing the convolution is maybe too big. So you'd like to reduce the size of the image. So this is a common practice in convolutional neural networks. And the interesting thing is that there's many variations on this convolutional neural network. So I'm giving you the generic version of it. So we'll take the results here and we'll pool them. So this is not something we train by neural networks. We take most commonly a 2 by 2 window here, and we replace the 2 by 2 window with a single pixel. And that pixel is usually the maximum because the maximum extracts the features the best. And then we do the same thing again. We take this new image after the pooling and we do another convolution on it. And we do some more pooling, and we can actually generate this to a number of different layers. Each one of the different layers then does something. What it's doing is not known yet. We get to the end, and then we have a final result, and then we run the final result through a neural network that gives us a possible a list, if you will, of potential outputs. So with everything, we have images and we have targets. So we have, in this case, maybe a picture of a bunch of airplanes, and we're trying to determine some sort of diagnosis of that airplane, whether it's healthy, whether we should set up an alarm, whether there's damage, whether it's dangerous, and we label all of these images, and then we train the neural network. But what are we training? We're not training on the pixels. We're training on this moving window that moves across the image. And so therefore we don't have to generate each of the pixels. This was an incredibly big breakthrough because it addressed the cursor dimensionality really, really nicely. So that is the idea of convolutional neural networks and the way they work. And they're used extensively. One of the big ones was in radiology, where they found out that these convolutional neural networks were able to detect features, abnormal features in X-rays and other things, maybe better than a human being. And they haven't replaced the human being, but they have turned out to be a great tool for the radiologists. So that's the convolutional neural network in a nutshell. And not going to go through the math, but I hope you can see the geometry of what happens and how the cursor dimensionality is determined. Another way that the cursor dimensionality can be addressed is through something called principal components. And this is a common statistical method wherein if you have data like this, you see on this ellipse with a bunch of these dots and stuff like that, you would see that, well, you know what, maybe this isn't two-dimensional data. Maybe this is one-dimensional data. And this we can take all of these dots and there's not too many variations in the second direction. So therefore, let's just project everything onto the green line here and just ignore the second dimension. And this extends to higher dimensions. For example, we could have a bunch of data in higher dimension that lies on a plane. This corresponds to the fact that this data is correlated with itself. And there are common things. And unlike the cursor dimensionality, these dots are not spread out over the space. If they're spread out over the space, we do have what? We do have the cursor dimensionality. So we need to play around with that. So one of the ways to do this is as follows. In 2 dimensions, we can actually generate a matrix of the data, and we have the input and we have the corresponding output. And what we can do with this matrix is we can generate the eigenvalues. And some of the eigenvalues are big, some of them are small. If you have a small eigenvalue, that means the dimension in that direction is very flat. If you have a big eigenvalue, it means it's spread out. So if it's spread out, what you want to do is you want to keep the dimensions that are spread out, and you want to throw away the little ones. Now, there's no exact way to do that. It's a fuzzy decision. You have to figure out how much you want to reduce it. But this is kind of cool because what this does is it reduces the dimension of your training. Because in the left case here, the 2-dimensional data now becomes essentially 1 dimension, and you can put it on this 1 dimension. And this 3-dimensional data becomes 2-dimensional. And maybe this 3-dimensional data lies on a line here too. Maybe that's enough to throw away. Throw away the third dimension, only keep 1 dimension. And this is available in principal component analysis. And once we do this, we can actually take any training vector, run it through this principal component matrix, and we can get a much smaller vector. And this smaller vector is the new coordinates of the system on the subspace, if you will. So if this was 3 dimensions, we might get this down to 2 dimensions or 1 dimension, and you could determine this by principal components. There's a challenge to this, however, and the challenge is the principal components are linear. And therefore, they're only able to look at data which lie on a line or data which lie on a plane. And sometimes the data lies on really weird manifolds, manifolds like this. Suppose all of our data lied on this manifold. Principal components wouldn't work there, would they? Because it only does things which are planar. So neural networks and something called autoencoders allow us to do this. Here's another example. Suppose that we wanted to look at weight versus height. W, the weight is equal to some constant times the height cubed. We would not be able to learn this curve using principal components if we have a big spreadsheet of data with the W's and the H's. We would not be able to do that. Why? Because it doesn't lie on a line. It isn't linear. And so principal components would not apply here. So here's the idea of using a regular neural network for doing this. It's called an autoencoder. The autoencoder is just like a neural network that you've seen before, except that we have an input. We shrink it down to something called a latent layer. This is a smaller layer. And then we train the output to be equal to the input. Now, this is curious. Why would we train the output to be equal to the input? Well, it turns out that if we come up with a neural network where we can train the output to be equal to the input, then the output, instead of being determined by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, instead of it being determined by 10 numbers, it's determined by 4 numbers. Why is it determined by 4 numbers? Because these 4 numbers are sufficient to generate the output again. So therefore, we have taken 10 dimensions, we have reduced it to 4 dimensions because this 4-dimensional latent space here, the waste, if you will, of the neural network, contains all of the information that we need to reproduce this input at the output. Now, what happens if you make this too small? What happens if you say we had 2 neurons here? Then this wouldn't train. We would never be able to train the neural network to this. And we can make it too big too. We can make this latent or middle layer much larger, and yeah, it would work. So the idea is to find the smallest hidden layer, which will allow you to generate your output from your input. So sometimes this is called an encoder. The middle layer is called the latent space because the latent space has all of the information you need for all of your training data. You take all of your training data and train this encoder to give the output, to give the same output as the input. So this latent layer contains all of the information that you need to know about your training data. And that is really very good stuff. And we can always look at the error, just like in regular neural networks. We have the input and we have the output. Turns out that the output, well, we'd like the output to be equal to the input. And the difference between that is the error. And we use that to do the error backpropagation in order to train the autoencoder. One place that this is useful and that it has been used quite a bit is in novelty detection. And I'll give you an example here. Suppose that we wanted to train a neural network on dogs, and we had all of these dogs here. And by the way, we use this for a neural network, a regular neural network. This could actually be a convolutional neural network too. We could actually take these convolutional neural networks, we could shrink it to a very small one and then expand it back and see if we got the picture of the dog again. But the difference between the input and the output is the error. And let's assume that we have a set of training data with a bunch of dogs, and we're able to train this autoencoder so that the output is equal to the input. And that's very good. And what does that mean? What does it mean about novelty detection? This means if you put in something different than a dog, so you put in an alligator, for example, after you've trained the autoencoder, what's going to happen? If you put an alligator, it's not going to give you an alligator at the output, is it? Dogs in, dogs out. Alligator in, who knows what's out. But whatever you get out, that's going to be a big error between the alligator and whatever the output of this encoder is. So if this error is big, you can be assured that whatever you input is not a dog. And so therefore this explains novelty. And why is this important? We talked about in the beginning the classifying me, all of the Bob Marxes versus things that were not Bob Marxes. Well, there's lots of things which are not Bob Marx's. In fact, it'd be ridiculous to try to train a neural network on Bob Marx's versus things which were not Bob Marx's, because not Bob Marx's is everything else in the world. I I use a joke sometimes when I'm giving directions to my house in Waco, and I say, "Okay, here's directions." I said, "You know where the Alico building is downtown?" And they said, "Yes." And I said, "Well, it's nowhere near there." So I could actually give directions to my house by giving them the street addresses and stuff, or I could give them all of the places where I don't live, and they could deduce where I do live. Well, that's not practical, is it? And it's the same thing with pictures which are not Bob's. So this is very good. We actually did work on this with Spectrum, and we were training it on Spectrum data. And here's the thing: if you train a regular neural network to determine, say, a dog versus a cat, then that neural network will give you an output no matter what your input is. If you give it as a dog as the input, well, it'll give you, yeah, this is a dog or this is a cat. But if you give it a picture of a kumquat or a watermelon, it'll still give you an output. It'll classify it as a dog or a cat. Well, you don't want that. You don't want false information being fed into your neural network that gives you an output corresponding to a kumquat, is calling it some sort of dog or some sort of cat. So therefore, what you can do is take your original cat dog data, you can train an autoencoder, and before you present a picture of the dog to the neural network, you run it to the autoencoder. And the autoencoder says, yep, the error between the input and the output is small. That is a dog or a cat. You're safe to proceed to give it to the neural network. So this is novelty detection, and autoencoders are very, very good at doing that. So here's an example. You can actually train it with noise. And this is an autoencoder trained with noise over a certain window. And after training it with this Gaussian noise for a while, it turned out that the autoencoder was able to recognize the result. And if we did something different, if we put a little blip in here, say for example it wasn't Gaussian noise, the error, bloop, oh, that's not Gaussian noise, bloop, that's not Gaussian noise. And it was actually pretty cool in determining signals buried in noise. So here on the bottom left, we have Gaussian noise riding on a very small amplitude sinusoid. If you look really carefully, you can see that there's a sinusoid there. We ran it through the neural network, and you'll notice when the sinusoid gets near zero that the error is pretty small. When the sinusoid gets near a peak or a valley, the autoencoder says, the area is really large. I don't think we can trust that as pure Gaussian noise. So the autoencoder is really cool in being able to do that. Another application, another feature is that there is implicit learning in autoencoders. For example, if we trained it with Gaussian noise, and we trained it with a Gaussian noise with a certain mean and a certain variance, it turns out this is the error plot. So with the mean and the variance of the operating point, which is about right here, if you can see my cursor, it turns out that that is the minimum. And if we deviate, yeah, the error gets bigger. But notice if we deviate significantly, then the error becomes much larger. So it implicitly learns this idea of novelty detection that, that wasn't the case. And here are some other examples. This is another example. This is the sensitivity to changes in the means versus the changes in bandwidth. If you put band limited noise into an autoencoder, it will implicitly learn things which are not that way. So if I trained on directions to all of our houses, and then we put in the Alico building, for example, it would give us a big error on the output. And so we can see that there's kind of an implicit learning of things which are what we want and things which are not what we want, which many times are too big. Here's another application of the autoencoder. If indeed you can take the dimension of the input and you can squeeze it down to a latent layer, that means that these data here are correlated. They're related some fashion, right? They're related some in some fashion. So you shrink it down and you get the result out here. So what happens though in the playback after it's trained? You give it some sort of input, but for some reason you've lost these two inputs. Well, if these two inputs are in some way related to the other inputs, then maybe this latent layer will contain the information to reconstruct this in some fashion because there is a correlation. Now, it could be that isn't the case too. If these are totally independent data with these other things and there is no correlation, it isn't going to work. But if there is a relationship, that is going to work. Here is a schematic of the idea of using an autoencoder to generate missing data. So we have down here, this is the known data. You see the known data in the autoencoder. This is the missing data. We have the known data and we have the missing data here. And then what's going to happen is we're going to run it through the autoencoder. We're going to get an error, right? Well, that error is fine, and that error is going to be big because, shoot, we don't know what to put in for the missing error. But now, after running it through the autoencoder, we have an estimate of what that missing error is. We don't know if it's right, but we know that there is an error there. And so what we do is we take the output of the autoencoder at the missing level, and we don't use well, we know what these other ones are, so we stick these known ones back in. We use the estimates from the autoencoder in order to generate the results. And then we run it through again. And we use the missing sensors, whatever the output of the autoencoder says for the missing sensors we use here. And then we iterate, and this is a search algorithm. We want to minimize the error. We want to find the missing values. We want to find the missing values from the known values as best we can. And again, this is not always possible. If the missing values are totally independent, it doesn't work. So this is an example of an autoencoder. We actually use this in a project at Boeing where they put all of these accelerometer sensors on an engine. And what they wanted to do is detect failure modes for the engine. And guess what failed most on the engine? It was the accelerometers, which actually failed the most. So we have all these accelerometers. We use this in order to determine the health of the image, but then boom, this accelerometer goes out, boom, this accelerometer goes out. So we have all of this, we have the known data, and then the ones that went out were the accelerometers that failed. And if you place these sensors around the engine, you can just imagine that some of them are going to be correlated to each other. If you have two accelerometers close to each other, they're going to have very similar readings. And so this was able to be used in order, this autoencoder idea is able to be used by taking a bunch of healthy data, training the autoencoder. And then once the accelerometers started to fail, we could actually estimate in many, many cases what the readings from the missing accelerometers would be, which is very interesting. Okay, so these are different variations on neural networks and AI, and I want to go through now some other applications of AI, which are very popular. We've seen this before. This is which are fake, which are real, and we determined that the four on the right were fake, and the four on the right, I'm sorry, the four on the left were fake, and the four on the right were real. And this is done using a generative adversarial network. And there's two ways to actually generate these fake images. This is one. Here's the basic idea behind GANs and also diffusion. These are ones that are able to generate deep fakes. We have training data, which is a picture of a bunch of faces. And if you think about the space of all faces in the world, all, not all the faces, everything in the world, we have pictures of my toenail, we have pictures of a door, we have pictures of the Alico building, we have pictures of Baylor, we have pictures of a number of different places. It turns out that the space of all faces is going to exist in some region within this enormous space of all images. That the set of all faces is going to exist in this small area in the space of all images. And so we can kind of sample this space. How do we sample this space? We sample it by taking real images, and this gives us ideas here of real faces. And so this face belongs here, this face belongs here. This could actually be done at a pixel by pixel level. And we are going to have to do a bunch of those. So our idea is, in order to train artificial intelligence to interpolate under this space, the original training data identifies the space, it identifies the silo in which we can play. And then if we identify this very nicely, we should be able to do something. Now, you'll notice that a watermelon will never be used in the training of this neural network. It just has to be faces. So we can't spoil it with the use of things which are not faces. So here's the idea. We would like to be able to identify this space in some fashion. And if we can interpolate and find other things in this same space, they will also look like faces. This is a general hand-waving description of what these deep fakes are trying to do, at least at this level. So let's talk about GANs first of all. GANs were a big deal. They're called generative adversarial networks. And here's the steps. You start with training data set, real photos of faces or cats or digits or something like that. And these are real examples that the discriminator works from. There's two aspects of the GAN. There's the discriminator and the generator. Okay, the generator begins by taking random noise, random numbers, and turning it into an image. This is pretty astonishing. At the start, these images are basically garbage, static, or blurry, or nonsense. And then it does the following. We have the real images. The real images are used to train the discriminator. And then the generator is something interesting. The generator is fed noise. We're going to see noise playing a big part here. And the generator is a neural network whose the structure of that net learns this little island of faces or whatever you're trying to generate. And that's what it's trying to do. So we're trying to train this generator to interpolate within this space of all of the faces. And so, how do we know that if this generates a good face? We feed it random noise and then we get an output. That output is fake images. In the beginning, they're going to be just totally garbage. So, we're going to be giving it to the discriminator, which was trained by the real images. And the discriminator is going to say, well, no, this doesn't make it. This doesn't make it. So, once a decision is made, you go back and you re train the generator and say, nope, that's bad. Remember, the output of the discriminator is either a 0 or a 1. This is a face, this is not a face. So what we want to do is we want to train the neural network using error backpropagation to generate more and more better. That's not good English, is it? But to generate better and better images. So as time goes on, this is indeed what happens. So that's step 1, step 2, and then step 3 is the discriminator is shown two kinds of data. It's shown real images from the data set, and then it's shown fake images from the generator. And that's exactly what we talked about. So the discriminator judges real versus fake. And it outputs a 1 if it thinks the image is real, a 0 if it thinks the image is fake. At the beginning, the discriminator is much better at its job than the generator. So that's step 3. Step 4 is adjusting the discriminator weights so that it gets better. We did the generator before. Now we do the discriminator. It gets better at calling real images real, and it gets better at calling fake images fake. So these guys are battling each other. The discriminator is getting a little bit more acceptable of what it can accept, and the generator is generating things which are more and more like the images in the original training set. And so we update the discriminator, then we update the generator, we freeze the discriminator's weights and train the generator, and it just goes back and forth. The generator makes new fake images and the discriminator evaluates them. And it goes back and forth. And here is a nice schematic of indeed what happens. So the bottom line is that the GAN is a battle between generator and discriminator. And it was really an innovative idea because usually we thought about the input of a neural network as what? As something which is meaningful. No, here we're having the input of the neural network, the generator, just being random noise. And then we're going to train the generator to take that random noise and to make it into an image. This generator is a neural network, so the structure of that neural network is going to form around things which generate faces in our example. And that was really a big breakthrough. The generator is rewarded when the discriminator is fooled. The generator updates its weight so that the next batch of fakes will look a little bit more realistic. So it's a battle back and forth and back and forth. And then we repeat this process a number of different times. Train the discriminator using real and fake images, and then this loop runs many times. It's just like any training, and it uses error back propagation. The discriminator must get better to keep up. Both improve through competition. Now it turns out there's oftentimes stability issues in getting the GAN started, and it's difficult to get the GAN started sometimes, and that's one of the challenges with it. But when it does work, it works very, very well. It actually reminds me this battling between the discriminator and generator of a verse in Proverbs where it says that iron sharpeneth iron, iron sharpens iron. So a man sharpeneth his countenance of his friend. So if you have two people going back and forth in a discussion, you both hopefully get somewhat better. Now, it turns out that GANs were used for quite some time, and then there was the idea of using something called diffusion. Diffusion does something very similar to the GAN, but it does it in a more stable way. And it turns out that if you look at images generated by Grok or ChatGPT today, they do not use GANs. They use this idea of diffusion. And again, it's the same idea. They're trying to do the same thing, take a bunch of images in a silo, and from that, once you've learned the silo, generate very nice fake images. So it's another way to do the same exact thing that the GAN does. So here's the training. The training goes forward and it takes all of your training data, and at different stages, it begins to add noise. So here's original training data. We add a little bit more noise, a little bit more noise, a little bit more noise, a little bit, until we get to a point where it's totally incomprehensible. It looks just like random noise. So that's the training. That's the forward diffusion. We trained the neural network to do that, to take images and make it into random noise. And then the diffusion process is an inverse process that takes noise and turns it back into an image. And it turns it back into an image which is in the silo. So this is the generating. So we would start with the generation. It's kind of training, and this is the playback. We look with noise, and different noise is going to give us different images. So we start with noise and we begin to go through, this is called a Markov process. This going from here to here is adding noise, here to here is adding noise. So what it actually does is it takes the output at one point and it actually forecasts, it predicts the noise which has been added. And it forecasts, it predicts the noise which has been added, and then it goes back and subtracts that noise from the original image. And it does it again and again and again. So here we have something, and after it's trained, it says, well, this looks like the noise in this final step here, and we're going to take that noise and we're going to take it away. And so we subtract that noise. Then we're going to take this, we're going to use that to generate the noise which was used to generate this, and that we're going to subtract that noise and get something which is better. And then we're going to keep on doing that. And it turns out that we get something back which was originally in the silo of the original images. So this is very interesting. So that's the overall view. That's the overall view. And by the way, this bottom line is just one that I made. This was synthetically generated process. It's really not representative of what happens. It turns out that you get certain features at different levels starting to pop out. It isn't a gradual improvement. So you start with real images, and you begin with a data set of real images, such as dogs, landscapes, ugly people eating bananas, insecure people trying to look cool, anything you want to. And these are the examples that the model is trained on. These are examples in the silo that you wish to isolate. And what you do is you begin the forward diffusion process. The model slowly destroys each image by adding random noise in small steps. And so you start with an image, you get slightly noisier, and each one of these steps is noted in the neural network, and then it gets more noisy, very noisy, and then you end up with just pure noise. And you do this with all of the data in the training set. And by the final step, the image looks like totally random noise. There's a reverse process now. Once we train the neural network, how do we get back an image in this silo? Well, we take a noisy image, and by the way, we start with just totally 100% noise. And the neural network says, you know what, this image, it looks like something that was noised up. So I'm going to estimate the amount of noise that was used to muddy this up. And so you estimate what that noise is and you subtract it from the noisy image. And that removes a little bit of noise. Then you do the same thing. You say, well, this looks like an image that looks like it should be noised up, and here's an estimate of what the noise is. And you get a little slightly cleaner image, and you just repeat this again and again and again. And in each step, you're asked what noise was added at this step. And then if you remove the noise, what would the image look like? So in each step, after the diffusion model is trained, it can estimate the amount of noise which is added to the image and therefore get a better image. And over many examples, the model learns how to denoise at every stage. And here's the basic idea of the generation. Once trained, the model can create two images. It starts with random noise, it removes a tiny bit of noise, removes more noise. And each one of these, as I mentioned, this process, this picture I have down here is really not representative. But you remove a tiny bit of noise, you get a slightly structured pattern. You remove more noise, you begin to have shapes appear, objects appear, and then the full image emerges. So it's just not a gradual improvement. By the way, for convolutional neural networks, this is also true. It turns out that most stages of convolutional neural networks, the first layer does edge detection, and the second layer does a combination of these edges. And in fact, there's a lot of work done in convolutional neural networks where people say, well, that first layer does the same thing every time. So I'm going to take the layers of the convolutional neural network over here, and I'm going to use them for my neural network. And they used the the layers for their neural network to generate their results using the layers from previous neural networks. Because again, with convolutional neural networks, the steps in the first two steps, or the steps in the first few layers of the convolutional neural networks typically do the same thing. They're edge detection and then uh, places of edge. They do the edge. So thus, diffusion, here's kind of a summary. A diffusion model destroys images by adding noise, then learns how to undo that destruction. It does the inverse process. And just like the GANs, the structure of the neural network learns the structure, the limitations of the structure of the image that you want to generate. And that is totally within the neural network. The input to the diffusion model is a random noise generation. Wow. That's kind of interesting because you usually think of the input and doing some sort of classification. No, the neural network structure actually learns the what is needed to generate images within the silo, which is defined by your training data. Uh, Training teaches the model to remove noise step by step. Generation times it starts from pure noise and reverses this process. And if you can imagine the number of different types of pure noise that you can put into a diffusion model, or if you put into a GAN, my goodness, that's a lot of faces if you've trained with faces, right? If you think of each distribution of noise just randomly generated as corresponding to a face, wow, you got a lot of faces. So you've really, really filled up this silo of training data. So this step-by-step denoising creates new images. So the last thing I want to talk about is, and again, I apologize because we're going fast, is the idea of transformers. This was generated in 2017 by some Google people, and they said all you need is attention. This turned out to be an incredibly big step because before that, in the syntax of things, you only looked at syntax of closely related objects. For example, in the autocomplete that you have in your cell phones, it only looks at recent values. And what these attention models did is they allowed us to look at relationships of words across many, many tokens, not just adjacent words, but everywhere. So, first step in the LLMs is to convert word into numbered tokens. Uh, a, Not a word, but a token. A token is breaking up words into different itty bitty pieces. So, token is two tokens, one for toe and one for kid. So it breaks it up into a number of tokens. Large language models have from 32K to 200K list of tokens. So that's their library. They have from 32,000 to 2,000 different tokens. These are utterances from the human language. And depending on version, modern Grok can take 250,000 to 2 million tokens in a query. So it turns out once that these are trained, even though they have 32 to 200K, then you can actually have a query that gives up to 1 million to 2 million tokens or words. We'll use the word words because I think that that's more understandable. And then there's something called context windows. You always wonder if you go to a transformer and you say, uh, tell me what mothers do. There's probably a context window that has some information about mothers, and it gives context to the word and expands your query to allow that greater context. The basic idea is to apply self attention. That's the core idea. This is what the people from Google said. And their original paper was All You Need is Attention, I believe, or Attention is All You Need, based after the Beatles song, as we've talked about. And the model looks at every word in the sentence and asks, which other word should I pay attention to when understanding this one? You notice in autocomplete, it only looks at your recent words. The transformers look at a much broader swath of words. And this answered one of the problems in artificial intelligence. In fact, Paul Allen of Microsoft formed the Allen Institute of for artificial intelligence in Seattle with big bucks. And he said the thing we need to do is we need to give artificial intelligence common sense. How can we give it common sense? Well, large language models address that to a degree. I still don't think large language models have common sense, but they have been able to simulate common sense. And one of the big obstacles that it overcame is so-called Winograd schema. Winograd schema are places where you have ambiguity in the sentence and the interpretation of that sentence is obvious from the context if you're knowledgeable, if you have common sense. So Winograd schema was the trophy doesn't fit in the suitcase because it is too big. Now, at one time, it was thought that these might be non-algorithmic sort of things. Well, it turns out that they are algorithmic, and that it turns out that large language models can indeed resolve now Winograd schema. So let's look. The trophy doesn't fit in that suitcase because it's too big. What's too big? Is the suitcase too big or is the trophy too big? It's obvious the trophy is too big, right? The trophy doesn't fit into the suitcase because it's too big. But if you're just going by English, it could be that the suitcase was too big. Well, that's not common sense. And it turns out that transformers allow us to do that because of this relation that they're able to give to very long areas, long sentences. Another one, the city councilman refused the demonstrators a permit because they feared violence. Now, who feared violence? Did the demonstrators fear violence? No, the city councilman did. And that's obvious if you have common sense. So we can see that indeed this Winograd schema were thought to be obstacles maybe neural networks could never achieve. This was addressed in Gary Smith's book. What was Gary Smith's book? It was called The AI Delusion. And he questioned of whether the Winograd schema could ever be solved. Well, it can be solved. Not only that, I collected for years flubbed headlines. I loved flib headlines because they're headlines that you read and there are two interpretations of them. One of them's funny, the other one is serious, and you know immediately which one is correct. But in the context of just the syntax of the sentence, you can't tell that. But large language models are allow you to do that. Let's let's look at a few of these. General who ran Vietnam briefly dies at 86. So it sounds like it could be that the general died briefly, or he briefly ran Vietnam, right? There's an ambiguity there. Um, the one after one, police squad help dogs bite victim. Well, how did it? What's the meaning of this? The police squad helps a dog bite victim. Did the police come and help the dog bite the victim, or were they looking at a dog bite victim? Again, all of these flipped headlines have a serious explanation and a funny explanation, and we know immediately what it is. But just applying regular grammar and syntax to it doesn't do you justice. It doesn't get you there. Third from the bottom, Iraqi head seeks arms. That's kind of cool. Um, and then here's some more. Second on the right, kids make nutritious snacks. It could be that you're a cannibal eating kids for snacks, or you're talking about kids actually in the kitchen. It's one of my favorite. Hospitals are sued by 7-foot doctors. Now, does this mean that they were sued by 7 podiatrists? Or were these really tall doctors that sued them? So all of these are just fun, flubbed headlines. And prior to 2017 of the large language models, these were unresolvable by artificial intelligence. In fact, there used to be yearly contest for the Winograd schema for artificial intelligence, and in most cases, it only beat it 50% of the time. It only, which is just basically a coin flip. So here, in a nutshell, is how these large language models work. Okay, so let's remind ourselves what the first step is. First of all, we convert each word into a token. We apply self-attention. And then the step 3 is we mix information from related words. This is using something called attention map. And the model blends information from important words. So here is a schematic, and the schematic is from the original paper. I think, but without the green and the red. And it shows what is needed in this multiple attention head span. And it relates the meaning of words in a sentence and is able to do that, first of all, for words close to each other. And this is what a multi-head attention is. So the first stage in a large language model relates the meaning of words very closely adjacent to each other. And then the next one does words, groups of words in relation to each other. And as we go through more and more layers, we get more and more in a relationship among the words. So it's autocomplete, first autocomplete, then it's autocomplete of the autocomplete, and it just expands and gets larger and larger and larger. And it works astonishingly well. In fact, it works much better than I think the original writers of the program thought. And if you've used any of these things, you know it works incredibly well. This is one of the reasons, by the way, that AI costs a lot. Number one is because of the number of tokens and the depth of training, and the more layers you add, the better result you get to a diminishing return. It is to a diminishing return. And I'll talk about that just in a second. So that's step three. And then step four is you pass through the feed forward layers. After attention, the models send each word's updated representation through a small neural network that feeds to the next stage. Step five is you stack as many layers, hundreds of layers, maybe thousands of layers. Each layer defines relationships and captures deeper structure and more abstract meaning. And just like the convolutional neural networks, where you first of all had the edge detection, then you had the combination of edges, et cetera. We see the same things sort of happening in large language models. The lower levels, you get grammar and short distance patterns. This is kind of the autocomplete. The middle layers actually do a larger attention span, and they do sentence structure and meaning. And then the higher layers actually do reasoning. I would say simulate reasoning, and they can do to a degree logic. And then step six is predict the next word. Despite all of this stuff, the large language models still act as a autocomplete. During generation, the model tries to answer based on all the previous words what comes next. And they do that with something called a softmax, where they take every word in the vocabulary and they give a probability to it. And this probability softmax it actually isn't a probability. It's more like a fuzzy logic, on a scale of 1 to 10. And it suggests the next sentence or the next word in the sentence. And you can see here dog is 0.32, cats 0.23, etc. And so sometimes it turns out that they don't choose the biggest, most high probable next word because that turns out to be boring. So they might choose the second or third. And this is one of the reasons also that you get different responses if you ask the same query a number of times. It's because in one case they might use the first one, the highest one. The second case they might use the next one, and of course, whatever they choose is going to influence what is chosen next. And so, therefore, you can get just a wealth of different responses from this. So it repeats this process one sentence at a time. So the takeaways, and again, time prohibits us from going through the math and the details of this, but the takeaways is that attention sees the entire sentence at once. In fact, entire paragraphs, entire pages. Early models can only see left, right, neighbors. That's in fact what your autocomplete is. Many layers capture deeper, meaningful meaning from the context. Parallel processing is also well, and it scales extremely well. Of course, you need more data. It turns out that the large language models have exhausted all of the fuel available from all of the literature in the world, and it works very well. So the last thing I want to talk about then is so that's kind of a mile high overview of large language models. So what about artificial general intelligence? Let me end on this. This is something which has been a theme throughout this course. Artificial general intelligence is something which reminds me of The Wizard of Oz, where AGI comes out and these people from OpenAI and Grok, Elon Musk, and who's a guy from OpenAI, Sam Altman, I believe. And they come out and they say, this is really great and stuff. They say AI is the great and incredible Oz. I hope that by looking behind the curtain, and if you've seen The Wizard of Oz, you know that's what happened. There's a guy behind the curtain, and that's the real wizard, and he's working all of these controls and pretending to be the great Wizard of Oz. And indeed, that's the case. If you attended a lecture by George Montagnez, very fascinating lecture, he mentioned something interesting. There is the theory that AGI is going to incorporate, is going to happen. It's just going to happen because we're getting better and better and better and better. And just because we get better and better and better and better doesn't mean that we are going to achieve AGI. It's kind of like Zeno's paradox, where he talked about a turtle that had to transverse a certain distance. And so the first step, he went half of the distance. The second step, he went half of the remaining distance. The next step, he went half of the remaining distance. So whatever distance remained, he just took a half step. And of course, Zeno's paradox says that the turtle never reaches the wall. Well, of course, that's silly because that's not what happens in reality. Because once you get down to microns, you can't take a half of a micron step. But indeed, it does apply to the case of diminishing returns, is what we have here. Dr. Montagnez mentioned that indeed GPT-1 was incredible. In fact, we talked about the news release that GPT-1 did that says, oh, this is so dangerous. We don't want to put this out in the world because we're afraid that it might take over. And then there was GPT-2, really great expansion, great improvement. GPT-3, yeah, that was really good. GPT-4, yeah, it was a little bit better. GPT-5, some people didn't even notice a difference. I mean, it was not that much. So we see that AGI is assumes that we are not going to have this diminishing returns. In his book, Ray Kurzweil talks about exponential growth. And he says exponential growth, there's Moore's law, there's the exponential growth in the computing power and all of this different stuff. The challenge is that there's really nothing in reality that is exponentially increasing. I used to say this about anything in reality. There is an exponential increase because somebody pointed out to me that inflation is an exponential increase, which is probably never going to end. But I think that anything physically, anything having to do with physicality, physicality, I don't even know if that's a word. Anything physical uh, cannot follow an exponential increase forever. And so this idea that we're going to get AGI because of this exponential explosion is going to be questionable. It does turn out that every time that AI comes out with a new algorithm, everybody gets excited, and they should get excited. I mean, GANs were really incredible because of the deep fakes. Diffusion improved on GANs. Convolutional neural networks allowed the generation of AI using images. We have large language models, which do incredible things. And by the way, the generator models are also used by Grok, I know. Grok actually used the transformer model in conjunction with diffusion in order to generate their images, which is one of the reasons that they generate them so quick. If you've ever looked currently at the case of Grok artificial images and OpenAI, ChatGPT images, you'll notice that Grok is a lot quicker, and it's because they have a quicker algorithm. I don't think it works better, but nevertheless, it's a really good algorithm. But here's the question: what's going to happen next? It isn't going to be that bigger is better, that large language models are going to take over, because again, we've reached a diminishing return. There are lots of people that believe that AI is in a bubble. At least that's the case when we talk. As we talk, there was there was a guy. Oh, what was the movie? It was called The Big Short, where there was this really eccentric guy who realized that subprime mortgages were in a bubble. And he was kind of wacko, but he was a genius. He was a savant genius about economics. Well, he recently bailed from NVIDIA and has said, yeah, AI is a bubble. Gary Smith, my economics colleague at Pomona College in California, said, yep, AI is in a bubble. In fact, Peter Thiel recently got rid of NVIDIA, um, saying that, yeah, AI is a bubble. And so we'll see. So if you watch this video 20 years from now, we'll find out if AI was in a bubble. What can save AI? The thing that can save AI is a new, better algorithm. As we talked in the beginning, all of the great advances in AI come from the human intellect. So we had like GANs, we had diffusion, we had convolutional neural networks, we had transformer models, and all of those came from the human intellect. Will there be something from the human intellect that can advance AI further? That's something which cannot be predicted. In fact, I have a prediction that the future of AI cannot be predicted. So we'll see if that indeed happens. Part of the this course was actually devoted to the idea of things that AI will never do. They'll never do the non-algorithmic because they are limited to silicon and they are limited to performing algorithms. So that kind of concludes the course and puts it in a bubble. And again, I apologize for going so quickly through the stuff at the end, but that's the way it is. The semester kind of disappeared. So with that, thank you for listening and be of good cheer.